So here's the next natural question. Follow me here for a second. Let's say we have an infinite chain of dominoes. This is an infinite chain of dominoes. I felt like cursive was good for the moment here. How do I write? Sound like that. Infinite chain of dominoes. Okay. I mean infinite. This line of dominoes goes on forever. Assume there's a flat earth that never ends, and there's just a bunch of dominoes that go on forever. Perfectly sliced up Brooklyn-style pizzas, all lined up. Just kidding. Just like regular dominoes, little rectangular things, all lined up, teetering, ready to go. Right? Let's look at two facts. Two facts about this scenario that I'm going to tell you right now. Or I'll say fact A, I will push the first domino over. Push, not pish. I will push D1 over. Let's go ahead and label these. So let's call, say this is D1, domino 1, domino 2, domino 3, domino 4, domino 5, domino 6, domino 7, domino 8, domino 9. Fact B. And this is the key fact to dominoes. And that is, if Dn falls, then Dn plus 1 will fall. Meaning that if you knock down the nth domino, the n plus 1 domino will get hit by it and will get knocked over. So if D4 falls, D5 will fall. If D5 falls, D6 will fall. Here's the claim. For all n the natural numbers, Dn will fall. And I'll even help us out a little bit. Let's go ahead and define P of n to be the predicate. Remember, it's a statement when you plug it in that says Dn will fall. And so this is equivalent. This is equivalent to, for all n and the natural numbers, P of n. Saying for all the natural numbers, P of n means the nth domino will fall. This is equivalent. Hello, Afra. And then this is equivalent right here to if Dn falls. So if P of n, then P of n plus 1 will fall. And then this is equivalent to P of 1. So how can you prove the claim? Like, this is on a homework. Where would you start? You'd probably start like we always start, right? You'd say, I'll try to prove there's something for all n. So let's go ahead and let n be an arbitrary / particular element in the natural numbers. We want to show P of n. So for real, like if you had to prove this, like what do you think you'd do next? I mean, what do we know?
Well, we know that the first one's going to fall, and then we know that if one falls, then the one after it will fall. So,
Yeah.
yeah, you know that.
So if we're trying to prove that P1 falls, we're done, right? I mean, we could say, like, by fact A, P1. If we show P2 falls, we're pretty good there too. We could say then, by fact B, P of 1 implies P of 2. So P of 2 is true. We can prove P of 2. All I'm saying here is, by fact A, we know we're going to push over D1, so D1 is going to fall. By fact B, since D1 falls, D1 plus 1, the next domino, D2 is going to fall. So that means P of 2, otherwise known as D2 falling, is true. Then by fact B, P of 2 will logically lead to P of 3. So P of 3 falls. And we could keep this going. But here's the problem. I want to do this for an arbitrary / particular element of n. So it's kind of weird. And this is what induction does. See, there's a lot of things in math that kind of work like this. Like, notice that here's how the proof would really go. We don't need to show, right? Because just like in the case where we had like P of n implies R of n implies S of n implies Q of n, we proved this for an arbitrary but particular n. We didn't have to go through and prove it for 1, and then prove it for 2, and then 3, and then 4, and then 5. We said just let n be arbitrary. Oh, it works for all arbitrary n? It works for any of them? Therefore, it must work for all of them. We have to show each one individually. We can show them all in one. We can show it all at once. And we want to do that same thing here. We don't have to write down all of them individually, right? We just want to show it all at once. And we kind of already have that. Right? Here's the idea. By fact A, P of 1 is true. So we know P of 1 is true. By fact B, P of n implies P of n plus 1 for all n greater than or equal to 1. I mean, it works just for all natural numbers, is what I'm trying to say. Thus, if we think about it, this works for all n. We already know it works for all n already. This forms a chain itself, implies P2 just by directly doing that chain. But then if we put 2 in for n, P2 implies P3. If we put 3 in for n, P3 implies P4. If we put 4 in for n, P4 implies P5. If we put 5 in for n, P5 implies P6. On and on and on and on like that. Therefore, by induction, P of n is true for all n in natural numbers. Here's the point. This proof is different. The reason it's different is because in a direct proof, right, you started with an n, and then you said, okay, P of n implies R of n implies S of n implies Q of n, and then you're done, right? We started with a particular n, and then we took it and we showed that connects to this statement, that connects to this different statement, which connects to this different statement. But here, we're not using different statements. There's only one statement here. There's only one predicate, one property. The nth domino will fall. But we know that the first domino falling will imply the second one falls, which implies the third, which implies the fourth, which implies the fifth falls, the sixth, the seventh, on and on and on and on like that. So we don't have different predicates here that's feeding into it. We don't have a chain of properties, of different properties. We have one chain of the same property, where the thing that changes is what we plug in. Here we had one in the whole time. We stuck with one in and said, for this n, P of n will imply Q of n. Here we don't have that. Here we're not, nowhere here did I even define an n. I never said like let n be anything, right? It's just that we know that based on how this fact A and fact B work together, right? These two facts put together will form this infinite logical chain. And since it forms this infinite logical chain, it will hit every integer along the way. Therefore, Pn is true for all n. And this is exactly what induction is. Induction is the process of forming this infinitely long logical chain and then saying it must hit all of them. And a lot of math works like this. There's a lot of things in math that's really hard to prove, like given an arbitrary integer, it's really hard to prove that it works a certain way. But it might be really easy to prove that if the integer before it worked, this integer will work. And the integer before that, if the integer before that integer works, then take that chain twice, it'll work. If the integer before that integer works, it'll work. Going all the way back to a base case. And we're gonna end it there today. Any questions? This is kind of weird. Does this idea of a proof make sense to you guys though? Then we're golden. This is really cool. This allows you to prove things inaccessible before. And in fact, this induction thing is baked into the foundation of mathematics. I've been telling you guys all along that there's like 8 assumptions that mathematics makes. Induction's one of them. You have to assume it works. You can't actually prove it works. It has to be there. Fascinating. Oh. Excellent question, Camille. Because the quiz has got to 5.2, I think. And we just started that. I'll check it out. Good question. I'll make an announcement if not. I made a lot of announcements this week. I hate making announcements. It feels like I'm not on the game. I'm not on top of the ball. But I'll eat my pride. Pride's healthy to eat. Okay, well, then we are done. No one has any questions? Fantastic class, everybody. Thanks for showing up. I hope this is making some sense. We'll do a lot more next week. And yeah, we'll be ready for a test.